Ladies and gentlemen, good morning. My name is Przemek Grzegorzewski. I'm a chairman on this special session, not special, just first parallel session. In the schedule, you can find 4 presentations. However, unfortunately, the second speaker has not appeared till that moment. So we have 3 speeches. We are a little bit late. Moreover, I add, if one of the speakers like to up to 5 minutes, so we'll land at the desired time. Okay, the first speaker is Alfonso Indurain. It is a joint paper having many authors. The title is Modification of Residual LSTM using a new approach to self-attention based on overlap and grouping functions. It's a paper prepared by the group from Pamplona. Alfonso, please, the floor is yours.
Yeah, whatever. Okay. Thank you for your presentation. Well, just to remind, my name is Alfonso Indurain. I'm from the Public University of Navarre. I'm going to present my work titled Modification of Residual LSTM based on a new approach to self-attention, based on overlap and grouping functions. This work has been done in collaboration with Javier Fernández, Miguel Ferrero, Laura de Miguel, and Humberto Bustince, also from the Public University of Navarre. How do I? Okay, sorry. It's working. I press on them. Okay. Oh. The pointer is working. No.
Okay.
Yeah. Wait. I think the back one is not working. To go back, it's not. Can only go forward. Okay. One more bubbles. Sorry for the delay. Before we dive into the presentation, I would like just to point out the skill of this presentation. First, I would like to introduce the problem that we have tried to face. Secondly, I will go quite briefly about some preliminaries, some technical, some more little bit of mathematical. I'm not an expert, so you will know more about them than me. Later, I will present the new modification that we are proposing, as well with the experimentation and the experimental result that we have done to test our proposal. And last but not least, I will end up with some conclusions and some future research lines that are going to be based on this proposal. So nowadays, there are, as you might know, billions and billions of data being generated daily, maybe even hour by hour. And data is always being stored digitally. And as this graph shows, there's expected to be an exponential increase in the data storage over the years. So let's face it, this trend is not going to change sooner. So the first thing that we might think is, okay, well, we need a lot of storage facilities to store all this data. But however, we already have these kind of facilities. The problem is that we have the facilities, but we don't have enough of them to store every single document in the planet in every single language that is being spoken at the moment. So that is the importance of the translation mechanisms that I'm going to talk about today. Okay, sorry. Oh, maybe that was the problem. So these kinds of mechanisms already exist and are usually based on the idea of recurrent neural networks. These kind of networks are based on learning from the past to try to predict the future. Okay, so. So when it comes to translation, recurrent neural networks usually use the beginning of the phrase, the first words, to try to translate the next word that is currently being studied by the model. Recurrent neural networks have an inner problem in them is that they don't usually work well when there are two phrases that begin with the same words but end with the different words. In this example, we might seem like I have the same phrase, but I've changed the end of the phrase so that it has a completely different meaning. And the translation generated is the same as in the previous example, yet for you that know Spanish, the translation is not very suitable in this case. So in this work, we propose to not only take into account the current word that is being studied by the model, but also the surrounding words of what we will call the context of the word being translated, which we hope will increase the performance of the network by changing the translation by giving it a little bit more information. So having said that, I'm going to talk just a little bit about the preliminaries. First of all, I would like to talk about aggregation functions. And as all of you will know, an aggregation function is an application that takes n numbers on the range 0, 1 and returns another number in that same interval. It must be not decreasing, the aggregation of 0 is 0, and the aggregation of 1s is 1s. And similarly, we have the AB aggregation functions, which is the same, but instead of on a closed interval 0, 1, on the closed interval AB. Next, we have the overlap functions, which are again an application which takes n numbers on the closed interval 0, 1 and returns one single number, and the properties that must be fulfilled are the ones displayed on the slide. And next, we have the grouping functions, which are nothing else but the end dual of the overlap functions and can be built as shown in this equation. Now I'm going to talk a little bit more technical preliminaries for those who know about deep learning. First of all, I want to talk about the word embeddings. Word embeddings is a mechanism to translate words into numbers because in deep learning, the only thing that the models are going to be able to interpret are numbers. So using word embeddings, we can translate, for example, the word cat using different characteristics into this vector of numbers in between -1 and 1 usually. Talking about deep learning, here's an example of different recurrent neural network families members. The first one is the baseline model, the recurrent neural network itself. Here we have the gated recurrent unit, and here is the long short-term memory unit in which we are going to focus now on. LSTMs or long short-term memory units have been present for a while, and there is a handful of modifications in the literature. One of such modifications are the residual LSTMs, which the main modification is that the output of the cell is going to be always influenced directly by the current state of the model. In this, if we are talking about translation, the current word being translated. So, as in equation 2, it's easy to further modify to not only take into account this current state or the current word being translated, but to also take into account the context that I have spoken about previously in the introduction. Oh. More or less, yeah. Okay. We already did this modification on a previous work where we presented the augmented residual LSTM, where instead of using the current state, it uses the A plus B state it's near the current one. We did this. We did this by using, instead of the equation 2, this new equation, equation 3, where we substitute the current state by an AB aggregation of the A previous states plus the B previous post states. But then we realized that this kind of modification has a little problem, and is that when it comes to translation, not every single word has the same importance. I'm not going to give the same word to the word no that to the word a, and this method of aggregation is not going to take that into account. That's why we took a look into the that's why we took a look into the self-attention mechanism, which is a mechanism well established in the literature of transformers to take input some data and generate new data characteristics based on the importance of its individual data input. So in this presentation, how to sum it all, to add it all up? Well, what we are proposing is to stick with the augmented residual LSTM and substitute the method of aggregation using a modified self-attention mechanism to not only aggregate the context of the words being translated, but also being based on their importance. The first problems that we face is that the self-attention mechanism takes n data inputs and outputs another n data inputs. And if we recall the structure of the residual LSTM, the input of the data must be just one single vector of characteristics. To solve this problem, we propose to include the self-attention mechanism inside a decision-making system, which will provide us with just one single representation of the whole context of the word being translated. So to do this, we are going to keep the first steps of the self-attention exactly the same. We will create two vectors called key and query, which are learned by the model itself. So they are usually randomized, and then we are later improving them little by little. The first step. Okay, the first step is to multiply the key and the query vectors by them, and thus obtaining the importance of the first word when it's measured against itself, and by multiplying the query vector by the key vector of the second word, we will get the importance of the second word when it's measured against the first word. These values are later on fed into a softmax, so that instead of having integers, we have what we call interpreted as weights. Once we have done these steps, we will have a row vector, a weight vector, which we can put inside a matrix. The second row will be created using the same steps, but instead of using the key of the query of the first input to create this, we will use the query of the second input. And so if we have 5 words, we will have a 5 by 5 square matrix. This is a bigger example of this matrix. The interpretation is quite simple. In this case, we can interpret it by rows. In this case, the first row represents how important is the first word when it's measured against the first word. The second column is the importance of the second word when it's measured against the first word, and so on. once we have this matrix, the only thing left to do is to select one of its rows as our weight vector, and then we aggregate the original representations of the vector of the words using a weighted mean, using one of these rows as the weight vector. But you will say, okay, but there are 5 vectors in this example. How we choose one of them? That's why we propose 2 decision-making systems. The first one is the most simple one, is to use the current word. The current word, meaning if in our context the word being translated is the 4th one, we will just take the 4th row of the matrix as the weight vector. And the second option is to select the most important word, which I will explain now. To decide which is the most important word, what we have proposed is to aggregate the matrix by columns, and thus obtaining a new vector. This vector, we can interpret it as a importance of every single word. For example, 0.2 is the importance of the first word, but regardless of what's measured against. So if we recall, this one is the importance of the first one measured against the first one. So 0.2, in our case, is the importance global of the first word. We did these aggregations by using overlap and grouping functions and some combinations of them. And finally, once we have this vector, we will say, okay, so in this case, we will take the highest value, the 0.7, and we say, okay, 0.7 is in the second position, so the second word is the most important, so we will take the second row of the matrix to do the weighted mean. To test this, our proposal, we have used a very simple data set, which has some phrases in English and the translations into French. These are the characteristics of the data sets. We are currently working on some bigger ones, but we don't have final results yet. Here are some results. These are the results obtained by the baseline models, the original residual LSTM, the original self-attention, and here is the original augmented residual LSTM, which we can see that we went up to 97.10 accuracy, more or less. And here is the new modification, mainly the one with the implying the most important word. We have achieved a slight improvement from the previous one and a bigger improvement if we recall the original baseline models. So to sum it all up and just to finish, in this work we have presented a new method to generate characteristics based on the importance of words so that we can use it inside a residual STM in order to work on some translation methods, some translation problems. As this graph shows, we have achieved a significant improvement from the original, from the baseline models. And here I have some future research line that we are going to do based on these results. First of all, we are currently working on a new architecture which is closer in shape to the original self-attention, so that we don't vary very much from it. And as I said before, we are already working on testing our model with our new dataset, which is quite big. It's the WMT16, which, let's face it, currently we are not able to work properly on it because we are lacking some kind of hardware, because translation is very hardware intensive. And last but not least, we will like also to test our problem against, our model against different problems such as sentiment analysis or some kind of multimodal problem. Here are some references that we have been using alongside this work. One more. So that's all. Thank you for your attention.
Consider the translation from English to French.
Yeah.
Have you checked vice versa later on?
Yeah, currently the dataset that we are working on now is the WTM16. It is some kind of text from the Euro Parliament. It has translations from English into a lot of languages and vice versa. And we are currently working from English into German and from German into English. So we have not arrived into the French one yet, but the results from German into English are quite similar. A little bit less, But we are also working on some kind new measurements, which is the blue score, which is more focused on translation. And nowadays, we are also trying to compare those scores with a transformer. We are a little bit behind at the moment from the transformer, but we are ahead from the LSTMs in a similar way as in this presentation.
Thank you. Yeah.
Is it here?
Maybe. Yeah. Okay. So the second speaker is absent, and the third one is me. So in a moment, you'll see the title, I hope. Yeah, I'm traditional way of showing something. It works, yeah, and it doesn't need electronics, yeah. But anyway, I have to combine this and that. Well, could you enlarge it? Almost. It's somewhere there. If you put this cross option to the whole screen, okay? Oh, exactly. Well, so the title of my presentation is Credibility Theory in Statistical Reasoning with Imprecise Data. Everything agrees with what you can find in an abstract book up to details. First of all, is my co-author is Ania Kozak, my PhD student, who helped me in experiments and graphs. And the second one is subtitle Meditation of FDA. Maybe it's not a usual thing, but before I would say something, I would like to ask you a question. FDA, it's an acronym meaning what? Fuzzy? No. Functional data analysis, yeah. Functional data analysis. Okay, so let's go on. Same problems. Oh, maybe. So motivations. We try to apply statistics to solve problems with imprecise data modeled by fuzzy sets. And as you know, there are many problems. Typical structure used for modeling data is fuzzy number. And we have problems with subtraction, with division of fuzzy numbers. Moreover, we have problems with ideas of distribution of fuzzy random elements. Finally, such things like central limit theorems. There are some theoretical, very theoretical, but nobody knows how to apply it in practice, yeah? That is why all the time we are looking for new methods, new tools, new approaches, yeah? Fuzzy set, fuzzy number, it's just a function in some sense. So the natural idea is, I need to, oh yeah. Can we apply functional data analysis methods for fuzzy data? And that is why I've gave this subtitle meditation on this topic, because I won't present such heavy results, but I want to convince you that in some sense it is possible. So maybe I can cope with, oh, it's, let's go on. Okay. Okay, we'll try. It's nice, but okay. So firstly, in 2 slides, we will have a short course in functional data analysis, okay? When we look on the progress in statistics, we may perceive this progress when moving from simplest to more and more complicated structures. For example, real numbers, vectors, functions, yeah? And this is the key idea that in functional data analysis, it's a group of methods and tools for coping with data expressed not as numbers, as vectors, but just as functions. Oh, yeah. So, roughly speaking, if we consider it as a sample, in traditional statistics 1 course, these are realizations of random variables, so these are real numbers, yeah? But now, our sample consists of n functions. Say, function of t, yeah? Usually, we define this function on compact interval, maybe on unit interval. Okay. Such fundamental textbook in functional data analysis was prepared by Ramsey and Silverman. If you want to look for such overview paper, I advise you Antonio Kevas in 10 years ago. Okay. Oh, mamma mia. So now more mathematical details, yeah? Suppose we have a sample space. Now it's really separable Banach space with some norm, yeah? Why separable? Because linear combination of elements, again, give us random elements, yeah? And what next? Sometimes we need inner product. So then instead of Banach, we just need Hilbert space. In practice, usually we, as Banach space, we consider a space of continuous functions with supremum norm, for example. In the case of Hilbert space, usually we use functions from LT space with such classical product. So this is a short course in functional data analysis. And now I hope we can cope with technical problems and move forward. Let's us go back to fuzzy world. As I've told you in the beginning, such a typical structure used for modeling outputs of experiment are fuzzy numbers. As traditional says, fuzzy number is such a fuzzy set defined on the real line, which is normal. It means there exists at least one element which surely belongs to the concept, which is fuzzy convex, yeah? So we have not valleys, yeah, but such mountains. Membership function is upper semi-continuous, and last but not least, the support is bounded. As we also know, there are two parallel representations of fuzzy numbers. One called LR representation, and the second one, LU representation. LR representation means we consider membership functions, and each membership function can be expressed by the following formula, where L and R denote two decreasing functions. So if I know these functions together with 1, 2, 3, 4 points, I know everything about such fuzzy number. Okay? The second representation, LU representation, means an infinite family of alpha cards. Yeah, this is a well-known definition of alpha card. So actually, if I know lower and upper bound, lower and upper endpoint of interval, because for fuzzy numbers, alpha cards are compact intervals. If I know it for the whole family, I know everything about this fuzzy number. Sometimes, especially in statistics with fuzzy data, it's not this direction. Instead of borders, we prefer to use the midpoints, and the spread means the radius of interval, but it's the same, again, two values, yeah? So these are two classical representations, which have many, many advantages, but also some disadvantages. Several years ago, Maria Angeles Hill, during her tutorial on my conference SMPS in 2018, she gave us such a question: can fuzzy data be treated as special functional data? And first her answer was no. Why no? Because such a direct application of some operations put us out of the context. What did she mean? For example, suppose I have two fuzzy numbers, this green and yellow one. This is a fuzzy sum through Minkowski operation, but this is the sum as we considered it as a functions in functional data analysis. So as you see, here we have fuzzy set. It is not a fuzzy set. The same thing appears when we consider multiplication by a constant. Yeah, this is according to Minkowski rule, and this is according to classical approach in functional data analysis. So directly, it's not the best idea, but as continued by Maria Angeles, indirectly, yes, we can follow treating this set of fuzzy numbers as a special Hilbert space on, in sense, some convex cone of a Hilbert space. And actually, the only paper I know devoted to fuzzy data perceived from the perspective of functional data analysis appeared, as you see, 6 years earlier. It was published by Maria Angeles, Ana Colubi, and Gil Gonzalez Rodriguez. But it's a nice paper. However, they all the time looked on fuzzy data through, in their case, LU representation. The paper is nice, but no advantages of such approach were shown there. That is why probably there were no other authors who continued this idea. But this problem make me to think maybe we attack the problem not from the best side. And I want to propose you another approach. So to question how can we apply functional data analysis to fuzzy data, I think we have to look firstly for another representation, maybe more useful for our goal, and then try to apply functional data analysis methods. Okay, so what I want to propose. ICR functions, what does it mean? Maybe, oh, okay. So suppose we restrict our attention now to continuous fuzzy numbers. It means fuzzy numbers having continuous membership function. It's not necessary, in fact, but just to make it easier, okay? And what next? Well, as you see, we have this LR representation. So first of all, suppose about extending both L and R function in such a way that before we have L on such interval and R on this interval. However, now, to the left of A, I put 0. To right of B, I put 1. For R, vice versa. 1 to the left of C and 0 to the right of X. Obviously, if I take extended L and subtract 1 minus extended R, I obtained our membership function. Yeah? But why I need this extension version? In 2007, in his book, Bading Liu considered an object he called credibility distribution. What's a credibility distribution? I use a little bit different notation, but using my notation, his credibility distribution is just the average of extended L and 1 minus extended R. Let's now look on such cartoon version of what I have told you before. Suppose this is our fuzzy number. This is part called R. This is the second arm or side called R. So I take this and extend it. So I have extended L. I take this part. I have extended R. Now I take 1 minus this. So I have such object. And after averaging, I obtain this green line. Of course, operation is one-to-one. It means knowing this, I can reconstruct our data, but it's not the end. Oh, okay. Now one comment to the paper of Liu. Why he considered credibility distribution? He considered it as an average of just possibility and necessity. I want to mention one more paper published 10 years later by Stefanini and Guerra, who considered, in fact, such a whole family of functions parameterized by lambda. So what we see in Liu's old paper, it's just for lambda equal to 1/2. But let's keep this solution. Now, suppose once more, I'll consider continuous fuzzy number, but now it's a subset called regular continuous fuzzy numbers. Regular means I have single element core. Again, it's not necessary, but just for ease. I can tell why, because I want to have no problems with inverse function, yeah? But of course, it's not necessary. Well, and so what do we have? We can prove easily a following theorem. A belongs to a family of regular continuous fuzzy number if and only if its credibility distribution is strictly increasing in unit interval, but moreover, A belongs to this family if and only if it has a unique inverse credibility distribution, which is continuous and strictly increasing. And this very object, the inverse credibility distribution, so denoted by epsilon, yeah, I will call as ICR. Once more, let's go to cartoon version of this theory. This is my initial fuzzy number. This is credibility distribution. And if I move my head a little bit and look, this is 1 and the second axis, I draw it here, I obtain such a curve, which is not decreasing. In this case, it's strictly increasing. It's disappeared. Oh, mamma mia. Go back. Oh, it's defined on unit interval. So as you see, if I have such a sequence of data, instead of such shapes, I will consider a family of quite regular curves defined on interval. For example, in our case, on unit interval. Okay? So after showing you this construction, let me try to convince you that it can work, yeah? I just show you a simple example. Suppose we have 2 samples of imprecise observations. Each sample consists of either n or n random fuzzy numbers. And we verify a hypothesis that both samples come from the same distribution. Again, that's not true. Very differently distributed, yeah? Okay, so what's our data? I have n realizations of x m realization of y. So altogether, I have n plus m fuzzy numbers. Well, if we have fuzzy numbers, following what I have discussed before, instead of membership functions, I can consider credibility distributions, and then there are inverse functions, so epsilon x and epsilon y data. Okay. Maybe our picture would look like that. X sample is denoted by red, y by green. Here, if I obtain such data, it seems they're quite well mixed. So maybe the null hypothesis about the common distribution is the true one, yeah? In this case, I'm not so sure, yeah? Because it seems like red being a little bit down in comparison with green, or in other way that green have some tendency, so second sample maybe reveals some tendency of taking bigger values. And last picture, oh, here is clear, yeah, that x's are generally greater than red. Okay, how to perform a test? The simplest idea is as follows. I consider this function pointwise, and in each point in unit interval, I compute the average, sample variance. Sample variance means, but for this very one alpha, yeah? The same for the second sample. When I compute the difference between typical values, so between averages, divide by something, doesn't matter. And last of all, I consider the biggest value. So it's like taking supremum norm. Yeah? And what then? I have to make some criteria for deciding whether this distance is big enough for rejecting null hypothesis or not. So since the distribution is completely unknown, I can perform a permutation test. Again, not. So I just pull these two samples into one. This means vector concatenation. So the first n elements belongs to the first sample. The last m elements belong to the second sample. Next, by putting asterisks, I denote a permutation. So I take a permutation of this original set. And now, before I pull it into one, now I divide it into two. Yeah. After taking permutation, I take the first n elements and called it the x, and last n elements I called it epsilon v epsilon y. Yeah, of course. Yeah. Exactly. And again, I compute the statistics, but now for this permutated vector. Yeah. And I perform these steps many times, say 1,000 times. Yeah. And finally, I look on the relation between the statistic value for each permutation with comparison to what I have obtained for original data. And this gives me opportunity to estimate p-value and to make the final decision. So as you see, the test construction is quite simple. And this is the last one slide. We have tried to look how it works when we enlarge the differences in location, as you see on these pictures. Yes, as you see, it of course works nicely. It just, as I mentioned at the very beginning, it was not a whole study of the properties of the test. It was just illustration. My main idea was to show you how to perform some more or less known methods from functional data analysis into fuzzy set data. So it's time for conclusions. In my opinion, it's the area which is worth for studying. And this representation through inverse credibility distributions for me is quite promising, and I may say I will continue this. And if somebody is interested, I'm open for collaboration. And last of all, because I feel some, because I'm a chairman, so I have to use my position, and I want to show you the last slide. For all of you who are interested in statistics, probability, data analysis, and so on, please join us in September in Salzburg in Austria. We have not first, 11th international conference. So you are welcome. Thank you very much for your attention. So are there any questions, comments, please? Yeah.
Using the
Mhm.
okay, but in any case, yeah. What this reminds this is very interesting. Yeah, if we really extend our imaginary and think how this can be applied. Yeah, look, so we have database for this database contains animals, yeah, say cats and dogs, yeah, right? And we would like, I don't know, to make decision which does not depend, yeah, on cats or dogs, yes. Yeah, and therefore we are looking for some unification, yeah, of this, yeah. And so in this respect, yeah, in my opinion, yeah, so yeah, if we have database and we want to make conclusions, yeah, independent on differences in this database. So in my opinion, so this can be useful, yeah. And this can be, for example, used also if we would like, yeah, to extract some say representative, yeah, on cat plus dog, yeah, in this unification, yeah. And so, for example, lecture, yeah, when dog playing, yeah, guitar, yeah, so something like that we also can have, yeah, using this approach, yeah. So if I'm wrong, yeah, or so tell me please, what's the main idea of this unification?
Opinion, we are not completely okay and not completely wrong, yeah, because indeed the idea was to consider different representation, but I looked on it more from mathematical point of view, yeah, just instead of membership functions or alpha cats, to consider structures which can be represented in Banach or Hilbert spaces, yeah. This was the idea. But of course, if I consider some parameters of cats and dogs, which could be expressed as a nice functions, yeah, it can be used. So this is why I've told you are right, partially and partially a little bit close. I don't catch.
You have told that your shapes
Mhm.
should be continuous and you show.
It's no. It's not necessary. Yeah, I just mentioned that I assume this in order to make this lecture more easy, to avoid some questions whether something exists or not. Yeah, but of course these functions may not be continuous. Yeah, of course this moment. Yeah. You're right.
Which are in fact something like distribution function.
Mm-hmm.
Again, we can have a left shape like distribution.
Yeah.
We have like a survival function.
Mm-hmm. Yeah, but in my opinion, it's more efficient in some sense to consider not functions defined on real, but it's better to consider inverse, just to consider on the same bounded interval. So if it's the question whether I have inverse or not, or how to define it, yeah, it's in some sense more, it's better for analysis, yeah. because generally these methods applied in functional data analysis were for functions defined on interval. Longer, shorter, yeah. Any more questions? So thank you very much. And now I change my role. I am again a chair of a session. I would like to ask Ms. Shivani Singh. She would tell us a lecture about RAF PDA, RAF CFG, and its application to healthcare system. So please. Oh, this is for you.
Yes. Yeah.
Hi everyone, I'm Shivani Singh. I'm a postdoctoral fellow at School of Information Technology, IIT Delhi from India. So I started exploring this area of rough set with automata theory. Automata theory is basically a part of theoretical computer science where we use the functions to compute. And one simple example we can see of automata theory is the lift we are using, because when we enter in the lift, so there are when we switch the input, we can go to next floor. So that thing where stages, because we are reaching from one floor to other floor, that are stages, and with input this transition is happening. So this kind of system where stages and inputs are involved is called the automata theory. So these are the contents of my topic introduction. I'm going to talk over rough push-on automata, its behavior, and then rough context-free grammar. Then obviously if grammar is involved, it will produce some kind of languages that is called rough context-free languages. And one more interesting thing is that we are going to find that this rough push-on automata has an equivalence with this rough context-free grammar. And then actually this area wasn't explored much in application part. So I was interested in medical domains. So I thought maybe we can look for some applications. So I tried this, and then it will be followed by the conclusion and future direction. So yeah, as I told you, automata theory is part of theoretical computer science, and it compute the functions. Also, it accepts some kind of strings. Whatever input is there in theory of automata, we call this inputs, and that is also part of language. So automata accept some strings that are going to be called as languages, and then formal grammars like English grammar. We have certain rules to form a sentence. So in computer science, we have formal grammars to compute programming languages. So they have also some kind of production rules there. And yeah, it is proven that automata is equivalent with formal grammars. But in my case, I have applied the rough set there. So I'll prove that rough push-on automata is have equivalence with rough context-free grammar. So basically in automata theory, there are four types of automata. These are the four types of automata which forms a hierarchy. The basic automata is finite state automata, in which only two components are there, stages and inputs. When we move forward, there is more powerful automata which is called push-on automata, in which I am working. Push-on automata contains one more component which is called stack variable, and it is used for memorizing something, because in many problems we need some a variable or a storage device to store the data. So push-on automata can store that. Linear bounded automata, in that we have stages inputs, but we can have more than one stack variable present there. And Turing machine, this is most of you must have heard about this. This is the most powerful automata. In literature review, I found that the basic automata, that is finite state automata, the rough set has involved there, and it is proposed by Basu in 2005. But unfortunately, after that, no further advancement has been done. and also there is no application, especially in the medical domain. So as we all know that my motivation behind the theory was that medical domain is full of uncertainty. When we go to the doctor, doctor also sometimes very uncertain when he prescribes some doses. It is also the case that with the doses there can be some side effects. So to cure this, they provide some extra medicines to tackle the side effects. So we need some kind of theory where we can incorporate certainty as well as possibility. So that structure is presented uh, in rough set theory. Okay, I think that is later. So rough set theory, most of you are familiar with. It is an approximation operator where lower approximation and upper approximation are there. Lower approximation has the certain certainty involved in the objects, but in upper approximation, they are possibility involved there. So my objective for the topic is that I want to incorporate that rough set into the automata theory in order to tackle the uncertainty, as well as to store something into the system. We need stack variable. So that's why I chose push down automata. So that is the topic, rough push down automata. And yeah, to develop it more mathematically robust, I worked on rough context-free grammar and languages and explored some closure property of that languages, and finally demonstrate its application on medical system, especially a case study over asthma disease. So yeah, this is the structure of push automata. We have stages, and with some input, the stack will change. So when the transition will happen, we are going to store something in the stack, or when we are going forward, we can push some objects into the stack. And if we at some point, like in medical disease, sometime it happened that any patient can go to from upper stage to lower stage also, because some medicine can control the disease, and the so we need the storage to again pop up those kind of variables, because when the severity of disease changes, we need the doses to be in accordance with the transition. So yeah, I introduced the rough set. Rough set is basically work on equivalence relation. We need a relation which is here indissolubility relation. So any object set together with this relation form an approximation space, and those approximation space contains the lower approximation and upper approximation. So yeah, so rough push down automata is basically a 9 tuple. So first is two, which is collection of states together with the equivalence relation R, and it will form the approximation space. Second is set of inputs, and third one is, and they all are finite set of states or finite set of inputs. Third one is the stack variable that is going to store something, and it will have also equivalence relation R dash, so that it can form approximation space there. I is definable set because yeah, in order to define the behavior of any automata, we need a state to start with, and we also need a state where we are going to reach. So it contains the I initial state and H is the final state. And also in stack variable, we need some initial symbol to recognize that the process has been end. If we reach to the that point Z naught, we will know that it is going to accept by the automata. So that is why the Z naught is needed. That is the starting symbol of stack variable. And the main thing is the transition function. In normal automata, this transition is happening with like normal sets, but here if we are in any state and we are giving it some input X, so it will go to the lower and upper approximation kind of state. So it will show that it certainly go to some state like Q1, but it also be the case that it can go to some state Q2 also. So certainty, so and the transition happen in form of lower and upper states. And accordance with that, we have also applied the roughness in the stack variable. So whatever we are storing, that will also go in the form of lower and upper thing, which means we are certainly storing something, but also there is a possibility that we can store something else. So yeah, this is the interpretation. Delta is the transition function. When you are in state Q with input X and the stack is containing Z, it can, the lower approximation is, it is showing that it can go to the equivalence class Pi of states with the rough stack variable gamma 1, which is again can be form of a lower and upper approximation. And the next is S upper bar, which means it can possibly go to the stage of equivalence class of Pj with the storage gamma 2. Yeah, that was the push down automata. In rough push down automata, we have changed the states with the equivalence classes and also the storage with the rough set of approximation of storage. So yeah, this is a mathematical definition of block transition map. So if we are taking the collection of the states, so that will be defined with the union of individual states. So if we want to the transition to happen on the set, so we need to go to the individuals and will then take the union of that. And this thing will happen in both the lower and upper cases. Similarly, if we can talk about the extension, so input is a collection of finite symbols, but it can also be extended to the infinite set of symbols by applying the, suppose here sigma is 0, 1, so they can concatenate it, with each other, and it can generate infinite strings of over the symbol 0 and 1. So that the sigma star we can use for the block transition map, it can extend it to the sigma star. In normal transition, we are taking the inputs from the sigma, but in the extension, we are taking the inputs from the sigma star. So it can handle the infinite strings. So yeah, if you are talking about the block transition map over the concatenation of strings, which means more than one strings are involved, then the transition will happen in a way that it will, if you are in some state, it will first process the first input symbol and reach to some other state, and then we will go for the next input to process to some other state. So it is a one by one process. So that will happen in form of lower and upper approximation also here. Yeah, this is the main thing. Any automata have some behavior which appears in form of a language. So here, rough push down automata have its behavior, but in form of lower and upper approximation. So here, gamma p bar is containing those strings or those languages which delta star lower having the non-unity intersection with the final state h. And these are the strings that are going to definitely accepted by the push down automata. And the upper gamma p bar is containing those strings that have upper delta star have the intersection with the final state non-empty, and that is going to be possibly accepted by the rough push down automata. So rough context free grammar. Any grammar have four tuples. In rough context free grammar, we have the four tuple, but in form of rough. We involve the equivalence relation and form the approximation space. So here grammar is four tuples. V is called non-terminals or variables. Sigma is called terminal symbols. S is the start symbol, that is a part of variable V, and rho is production rule. So the main part is the production rule by which we can produce terminals from the non-terminals. So here production rule are in form of rough set. So we have defined the lower row and upper row. Lower row is going to generate the non-terminal, lower non-terminal to the lower terminals, and the upper row is going to generate upper non-terminal to the upper terminals. So, and then this grammar generates the language which is RGW, and it will contain those inputs W, which can be reached from the start symbol S. So after a sequence of productions, if we can reach to some W from the starting state, those are collected in the this system and called the rough context free language. So we are reaching to the state where automata is also producing some languages, and here grammar is producing the languages. And uh, yeah, this context free language that has been defined have some closure properties. So union of two rough context free language is again a rough context free language. So the simple idea is that we are choosing a new starting state, and the first production is that new starting state will go to the starting state of variable v1 or variable v2. So after that, it will reach to the main string w. So this is just a hint that I proved in my paper. Uh, Also, concatenation of two rough context free language is again a rough context free language, and the star closure that I mentioned earlier is also of rough context free language is again rough context free language. So yeah, that is the part of equivalence where any rough context free grammar have the equivalence with rough push down automata. So the push down automata have the 9 tuples and grammar have 4 tuples. So the idea is that uh, with the transition function and the production rules, so we can define the transition function in a way that any unprocessed part of the string in push down automata will align with the stack variable of the automata. So, and also the process part that has to be going to give the input is aligned with the terminals of the production rule. So we are defining the transition in a way so that it can resonate with the production rules of the grammar. So this is also a hint. This is a very long proof. So main idea is that the process part of the input of the automata is resonate with the stack, and the unprocessed part will resonate with the terminals. And similarly, I have done in the reverse process also, that for every rough push down automata there is a rough context free grammar. Next. Yeah, because the time is limited, so then I applied these two theories on the healthcare system, basically on the asthma disease. This is a chronic disease. So how it can apply there is that, yeah, so this is the diagram of stages of asthma disease. So you can see there are lots of stages: intermittent, mild, persistent. So these can be considered as the states of the automata. So these stages will align with the states of the automata, and the medicines we are storing, because in every stage you doctor prescribes some kind of doses, and that needed to be stored somewhere, because next time when patient come, many of the time they don't remember what was given earlier. So this system will store the medicine in the stack variable of automata, and there are some factors which are the reason for transitioning the stage of the disease. So here in the asthma disease, the factors are like adherence, environmental control, or some kind of allergy. That is the reason of transferring from one stage to other stage, and that is work as the input of the automata. So that way it resonate with the automata theory. And yeah, I have collected some data from government hospital in India of asthma disease, and from with the help of this, I formed uh, a dummy data of asthma, because yeah, so there are lots of symptoms: breathlessness, cough, chest tightness, fever, and most importantly, spirometer reading. So based on these factors, doctor give the decision that the patient have the disease asthma or not. So I have collected some report with that. I found this data, and yeah, so that I explained earlier. The rough push down automata deal with this problem as the states there will align with the stages of the disease, and also if some patient have the same kind of symptom, they can go to one class. So that will form the equivalence relation or equivalence class based on the symptoms of the patient. And yeah, and sigma, which is input alphabet. I explained that we are taking two inputs here, 0 and 1. 0 means if there is no allergy, no irritant, no viral infection, which means it can happen that no transition will happen. But we are dealing with uncertainty. There might be some chance, although these three things are not present, but transition can happen with some other factors. So that will go into the possibility section of the approximation operator. And one is if either of the condition is presented in the system, which means definitely they are going to transition to some other stages. And the we need some initial state I and final state H to decide the behavior of the automata. And in a stack we are storing the medical doses, and again here you can see the M bar. M bar means if you are in stage P1, which is equivalence class, so the doctor will definitely prescribe the dose M, but to cure the side effect, they can also prescribe some doses E1. So this will go in form of M, comma M plus E1, which means lower and upper approximation of medical doses. Uh, then we developed transition rules or transition functions, how it can proceed with the transition from one state to another state. Like with zero input, because it is the possibility that no environmental control allergy is present there. So with P1, there might be the chance that the phi is representing that it is not going anywhere. It is still in the same stage of their disease. So we are not here. M oblique M is representing the medicine was M, but we are not changing anything because it is in the same state. But it is the possibility that P1 can go to the P2 stage. So we are going to push some medicine N over M. We need to add some extra medicine because the condition is severe now, and so this symbol N over NM is representing that N is over M in the stack variable. So in this way, I found this transition table. And finally, the behavior of rough push down automata that I defined earlier. So it is going to, with some experiments and with some calculation, we found that in stage P1, the push down automata is definitely going to accept some kind of strings that is in theoretical computer science are called languages. So gamma P1 bar, so these strings are going to certainly accepted by the rough push down automata, and gamma P1 upper bar, these kind of strings are going to possibly accepted by the rough push down automata. So this image I also use as ma'am used. I also use AI tool to generate imaginary thing. So he generated this kind of system of rough push down automata for the treating asthma disease or storing the medicine. So yeah, conclusion. So I developed rough push down automata and showed its application, possible application in medical domain, and uh, to more making it more rich mathematically, I developed some grammar languages and so the equivalence between automata and grammar. And for the future work, as we are dealing with the uncertainty, so we can also involve fuzzy set theory here to more precisely giving the membership degree of the approximations. So we can work on fuzzy set theory or fuzzy rough set theory or any other extension. And as I worked on rough push down automata, but there are two more powerful automata like linear bounded automata and Turing machine. We can also involve fuzzy set and rough set in those areas also. So that's it from my side. These are some references. Thank you.
Yeah, also, I was a little bit lost in my patients, has attributes and decision attribute, yeah? This lower and upper bound of graph set, yeah?
Mhm.
On which levels?
No,
How you-
so I developed an equivalence relation based on these symptoms. So you can see that X1 have the features if and decision is no.
Yeah.
So based on this decision
Yeah.
or features, we can form a equivalence relation. So some kind of
With correspondence to
yeah decision
decisions,
also.
we construct lower and upper bound.
Yeah.
Okay.
So, yeah, equivalence with
I know. More questions, comments? So thank you much more.
thank you.
So the speakers, the audience, and enjoy your break. Thank you very much.